All right, welcome to the Explainer. Today, we're getting right into the fundamentals. The absolute bedrock of physics. We're going to uncover the rules that govern literally everything that moves in our universe, from a tiny baseball to an entire planet. For centuries, these two simple questions completely stumped some of the greatest minds in history. But the answer, when it finally came, didn't just explain motion. It totally changed how we see the world. For thousands of years, the big idea, going all the way back to thinkers like Aristotle, was that an object's natural state is just sitting still. And, it kind of makes sense, right? You roll a ball, it eventually stops. To keep something moving, it feels like you have to keep pushing it. But that simple, common sense idea was missing a key, invisible ingredient.
So here's our roadmap. We're going to follow the same path of discovery that Galileo and Isaac Newton took. We'll start with the basics. What even is a force? Then we'll look at what happens when forces are balanced or unbalanced. And from there, we're diving into each of Newton's 3 legendary laws of motion to see exactly how they cracked the code. Okay, let's get into it.
Okay, first things first. Before we can even talk about the laws, we have to define the main character in this whole story, force. Now, you can't see a force. You can't hold it in your hand. What we see and what we feel are its effects. Just think of it as the invisible cause behind any change in motion, the very thing those early scientists were looking for. So a force is basically any interaction that, if it's not canceled out by something else, is going to change an object's motion. It can get things moving, it can stop them, it can speed them up, slow them down, change their direction, or even squish them, like squeezing a rubber ball. Okay, so if a force is just a push or a pull, how come when you push on a really heavy box, nothing happens? Well, this brings us to a super important idea, the difference between balanced and unbalanced forces. Here's the key takeaway. When forces are balanced, they cancel each other out completely. Think about a game of tug of war where nobody's winning. Both teams are pulling with equal force, so the rope doesn't move. The net force is 0. To get any change in motion, what scientists call acceleration, you absolutely need an unbalanced force. And there it is. That's the missing ingredient we mentioned earlier. When you first start pushing that heavy box, the invisible force of friction between the box and the floor is pushing back on you with an equal force. The forces are balanced. To finally get that box to move, your push has to be an unbalanced force. It has to be stronger than the friction pushing back. This right here, this is the massive leap in thinking that changed physics forever. Galileo and then Newton asked a brilliant question. What would happen if we could get rid of friction? If we could remove all the opposing forces, what is an object's true natural state?
This is revolutionary. This law says an object doesn't naturally want to stop. It naturally wants to keep doing whatever it's already doing. If it's sitting still, it's going to stay still. If it's moving, it's going to keep moving at the exact same speed in a perfectly straight line, literally forever, unless some unbalanced force comes along and messes with it.
So this tendency to resist a change in motion has a name, inertia. And how much inertia something has is all about its mass. It's that simple. That's why it's way, way harder to get a freight train moving than it is to get a bicycle moving. The train has a ton more mass, so it has a ton more inertia. You actually feel inertia all the time. When a car hits the brakes, your body wants to keep moving forward. When a bus takes off, your body wants to stay put, so you feel pushed back into the seat. In every case, your body is just trying to obey that first law. It's resisting the change in motion. So the first law tells us that an unbalanced force will cause a change in motion. But the second law? Well, the second law gives us the math to figure out exactly how much of a change. This is where physics gets its real power. To figure this out, Newton first came up with a concept he called the quantity of motion. We just call it momentum. It's a pretty simple idea. The amount of oomph a moving object has depends on 2 things: how heavy it is, its mass, and how fast it's going, its velocity. A bowling ball and a tennis ball, going the same speed, have totally different momentums. Okay, that's the official wording of the law. It sounds a little complex, I know, but all it's really saying is that the harder you push on something, the bigger the force, the faster its momentum is going to change. Now, this is the amazing part. How we get from that big, wordy sentence to one of the most famous equations in all of science. Let's just walk through it. The law says force is tied to the rate of change of momentum, right? That's the change in mass times velocity over time. Now, for most things, the mass doesn't change, so we can pull that m off front. That leaves us with mass times the change in velocity over time. And what do we call the change in velocity over time? That is the definition of acceleration, a. And boom, there it is. Force equals mass times acceleration, F equals ma.
Newton's third and final law of motion is, well, it's maybe the most profound of them all. It reveals this deep, fundamental symmetry in every single interaction in the entire universe. Now, we've all heard this phrase, but the physics behind it is very, very specific. It means that forces never, and I mean never, happen by themselves. They always come in pairs. You literally cannot push on something without it pushing back on you.
And here is the crucial detail that so many people miss. We're talking about two separate forces acting on two separate objects. When a gun fires, there's an action force of the gun pushing the bullet forward. At the exact same time, there's an equal and opposite reaction force of the bullet pushing the gun backward. The forces don't cancel out because they aren't acting on the same object. And once you get this, you start seeing it absolutely everywhere. To walk, your foot pushes backward on the earth, and in reaction, the earth pushes forward on your foot. That's what moves you. A rocket pushes hot gas down, and in reaction, the gas pushes the rocket up. It's always an equal and opposite pair.
And that leaves us with one final puzzle to chew on. If you go and push on a giant truck, the third law says the truck pushes back on you with an equal and opposite force. So, if the forces are equal, why is it even possible to move the truck? Why don't they just cancel out? The answer actually forces you to combine all three laws, revealing the beautiful interconnected logic of how our world really works.